parameters. Okay. This is for subdivision graph. This is a polynomial. And the Somber energy of the subdivision graph is if it is a regular graph of degree 1 only. Okay. Regular graph of degree 1 means only edges. Only edges. Okay. So you'll get the Somber energy of the subdivision graph, Somber energy of the line graph, semi-total point graph, semi-total line graph, and so on. Similarly, if R is more than or equal to 2, these are the expressions. Okay. I will go to the, this is not required. Here. Come to this one. Conjecture on the Somber energy. Recently, Ghanbari in 2020, he stated that there is no graph with integer value Somber energy. There is no graph whose Somber energy is an integer. Okay. Even ordinary energy also like that. If there is no graph whose ordinary energy is an odd number. Ordinary is an odd number. So reverse way we have to go. This is when k is a odd number. What about when k is even? For k is even, it is still pending. Okay? Still pending. Okay, so the case when k is an even integer needs further study. Okay? Hence, we have conjecture here, there is no graph, regular graph with adjacent energies 2k root 2, where k is a integer. Okay? So if the conjecture of the Somber energy is correct, this is correct. This is correct. Okay? So with this I will, then further this one, some chemical applicative, one slide. So Gautam Swami, 2021, they studied the correlation of the Somber energy with total pi electron energy. Okay, and they got the good correlation. Okay, they have shown good correlation. Okay, between the Somber energy and the total pi electron of a corresponding molecule. Then Rezovic and Gutmann studied recently the Somber energy of the Benzonaide system with a fixed number of hexagons. Okay, and they also observed that it has a good correlation. Okay. And in case of trees, they observe that there is a decreasing linear correlation between the Somber energy and adjacent energy. So here it is a positive correlation, whereas in this case it is a negative correlation. Okay, okay. Here it is increasing both. Here it is decreasing. One is increasing, one is decreasing, but having the good correlation above 0.9. Above 0.9 it is. Okay. So this introducing this energy has a meaning. So many such properties or many such method properties as well as the chemical properties of this concept need to be further investigated. Okay. Thank you.
Thank you, Professor. Students, you have any questions? It is a different topic as we witnessing from morning. It is related to graph theory. You people studied in discrete mathematics. If you have any simple questions, you can interact. And Professor Ramaneswar is so energized. After lunch, our students become so active with your energized talk. I am very thankful on behalf of our department and university and our wonderful talk. Sir, students can interact, especially we have graph theory students are registered under our colleagues. They will interact with you. Thank you for the talk, sir. Thank you.
Please, thank you.
So I thank Patil sir for sharing the session. Sir.
Oh, madam. Thank you. Now the next steering system is
So we're going to start the next session. So I would like to invite Professor H.S. Ramane sir from Karnataka University to share this session. So the first talk that we have from Professor R. Rangarajan from University of Mysore, and he is my research guide also. So I've become fortunate to hear sir now and then here. So because of these conferences, I can meet sir. So, sir.
Good afternoon to all of you. I welcome all of you for this session, and the speaker is Rangarajan sir. He got his BSc in PCM from the Yuvraj College, Mysore, then MSc from the University of Mysore in the year 1986. PhD from the Indian Institute of Technology, Madras in the year 1993. He has more than 27 years of teaching and research experience. He has guided 19 PhD students and 3 are under progress. He has more than 100 publications in his credit. He has done projects, delivered the many talks in the conferences, and he is very humble. Whenever we call, he is ready to come. So such nice person is here with us, and I request Rangarajan sir to please give the talk.
ಜಾಸ್ತಿ ಬೇಡ. Hello? Okay. So first of all, I thank the chairman of the session, Professor Ramane sir, for introducing, for his kind words. So I thank Professor Patil sir, Madam Chandrali. She said I am her guide. Yes, but nowadays it is the other way. She is the guide. Because I am partly working in graph theory, also partly working in the differential equation. So therefore I will be consulting her very frequently. It's very good mixture here. Narahari, Boregoda sir, they work in graph theory. So, but in our department I am only one working other than these main subjects, number theory and graph theory. So, but I am interested in everything because I have left only 1 year of service. So, it's worth learning all the subjects if possible. So, from the morning it was very lively here. Students are interacting very well, and the resource persons are giving the best possible invited talks are going on here. So I congratulate Patil sir for arranging such an excellent conference, also Narahari. So my earlier speaker, what is his name? Palla? He is here. Kiran. He talked about non-linearity. So what I have understood is, whenever a train makes a sound, it is a linear, okay? Or whenever a violin is played, or a tabla is played, they are all linear waves you are listening. Whereas whenever you see somebody shouting like me, it is non-linear. Or if you are standing near a seashore, the waves are coming towards you, you feel that it cannot be linear. But many will be very happy with the non-linear because nowadays loud music are preferred than the soft musics. It's only to sleep, not to jump and dance. So therefore the music which is played for jumping and dancing is non-linear, whereas the music which is going to make you sleep is linear. Okay, so next please. ಈಗ ನನ್ನ ಹತ್ರನೇ ಇದೆ ಅಲ್ವಾ ಅದು? ಓಕೆ ಓಕೆ ರೈಟ್. So I am going to discuss three equations. One is called Korteg-de Vries equation, another one modified Korteg-de Vries equation. So they are model equations in the field of partial differential equations, nonlinear dynamics and application. These are some of the references I have followed. So this is the called as one soliton solution, solitary wave, because there is only one wave there. We call it as a solitary wave. So it's nothing but a secant hyperbolic. So whenever you see a road hump, it resembles a hump-shaped curve. Next one, this is called as two solitons. So deliberately we have taken different amplitude. You can see as the time passes, the bigger one is going to collide with the smaller one. Is there a light I can show? No. There, okay, maybe, I don't know. Oh, yeah, it is coming. But when it is on that, it's not showing its color. See, it is here, but not there. Okay. Yeah? Too bright, yes. In the third one, both are colliding. So in the fourth one, slowly the smaller one will come to the other side and bigger one will pass. So it is like a particle behavior. Therefore we call it as soliton. So two solitons. You can think of multi-solitons. That's there. But my purpose is to only compute such one soliton solutions for three equations through using what is called as perturbation. Earlier speakers have shown lot of series. Pradeep Siddeshwar showed what is called as Maclaurin series. So our Kiran sir also showed the perturbation series. So I am also going to make use of it. So I want to skip some idea. This is from physics called as Lax pair. Better myself and Chandrali will discuss about it later. It's not suitable here. There is another transformation called Mura transformation. Okay, that is the second line. U equals V squared plus dou V by dou X. When you just apply it to KdV equation, it is a third order equation. You can observe. The first term is called the time evolution term. Second one is U into dou U by dou X is called convection. That's what our Kiran sir said. When you heat a water, suddenly you will get some bubbles and then it's called convective currents flowing inside your water, boiling water. So that's called convective effect. And the third one is called diffusion. So it disperses. It can't, but in a water vessel, it cannot disperse. The place is very limited. Whereas if you see the seashore, the sea water is also heated. We don't know, but we can't feel it. But otherwise the cloud cannot form. Therefore, heat current is there. Time evolution you can see because the waves are moving. And they are also dispersing. They will go back and disperse themselves again into the sea. So therefore, all the three effects combined together is called as this Korteg-de Vries. Both are German mathematicians. So Korteg is one mathematician. De Vries is another mathematician. We call it as shortly KdV equation. So this will split into same equation, you can observe. Therefore, it is called as modified KdV equation. ಯಾಕೆ ಬಣ್ಣ ಚೇಂಜ್ ಮಾಡಿಬಿಟ್ರು? Okay. So we want to discuss about what is called as this traveling wave solution. So it is a transformation which converts PDE into ODE, ordinary differential equation. So there are many types of traveling waves. So they are called as solitary waves, kinks, and just one shade will be there. One sharp wave will be there. It's called kinks. Also periodic waves are there. That's what our sir showed. Kiran sir, they are called periodic waves. And they are all the waves will be inside some box. They are called as compact tongs and so on. It's a beautiful book by A.M. Was, Partial Differential Equation and Solitary Wave Theory. So you can go through it. This is about a method called Adomian decomposition series. There are standard books on that. So we want to apply that to our equation. So we have generalized that KdV equation by introducing these three parameters alpha, beta and k, where k is this 2 times square. C is your velocity of the wave given by u of x minus ct. Okay. So we don't use epsilon here. So in the usual perturbation expansion we make use of epsilon. But Adomian suggests that you don't have to bother about such expansion. So every time you think that you are going to converge it, or maybe it is ultimately finite only, or at the most it is a convergent series. So when you substitute it, it reduces into this system of equations, and you have to choose the solutions. Instead of x squared, x cube, we will be selecting this e to the power of minus kz, e to the power of minus 2kz, like that. So we will be using the powers of exponential with negative powers. So therefore you are ensured of boundedness. So you can substitute and do some what Ramane sir said, high school mathematics. So you can just sum. If you do sigma, what is sigma n? It is n into n plus 1 by 2. If sigma n squared is, anybody? N into n plus 1 into 2n plus 1 by 6. If it is n cube, it is n into n plus 1 by 2 whole squared. Like that. So you can just do all those tricks. Very simple high school tricks. So you can simplify and see that you can express your am plus 1 easily, and it becomes a geometric series. You can apply, suppose you don't want to sum as it is, you can apply what are called Pade approximation, so that you can reduce it into secant hyperbolic square. I'll just leave you that to you, how an exponential function will lead to secant hyperbolic. What is cos hyperbolic? Anybody? E to the power of x plus e to the power of minus x divided by 2. Okay. So secant means 1 over 2 divided by e power x plus e power minus x. So that idea is there. That's all. I have squared it. Okay. So next I will apply it to MKdV equation. So suppose you subject to that traveling wave, it reduces to an ordinary differential equation. So it is a nonlinear equation. You can see that. In fact, if the derivative is first order, it would have been a Bernoulli equation. But it is not. It is a second order. The derivative term is second order. So you can apply this Adamian technique, the series technique. So in the usual perturbation, we take epsilon, epsilon squared, and some unusual functions. We take, most of the time it's very hard to reduce them. Therefore, cleverly Adamian says that you fix it such a way that you can easily sum them. So it's a type of match fixing. You have to work it out at the level of u0 and u1. It will automatically take you to un plus 1 by induction. And it is a type of convolution, you can see. A discrete convolution is there, finite convolution. So easily it reduces to a secant hyperbolic again. So we have done computation here for some values of A, alpha, beta and C, and we get the waves like this. This technique you can also apply it for coupled equations. So somehow I used to tell madam to work on these coupled equations. She is expert in it. She works on this predator-prey models, for instance. So if you can also mix KdV and MKdV, that is done by Hirota and Satsuma. So if you just put B is equal to 0 and A equals 1, minus 1, it becomes KdV equation. And if you say U and V, if you relate properly, it becomes an MKdV equation. So it's a coupled equation. I don't know, for some tension, I have prepared 60 slides. So most of them I will skip, don't worry. So what are this? This is the final solution I want. U should be secant hyperbolic, V should be secant, okay? So for that, okay. So I am using usual perturbation technique, not Adamian. So I will be transforming U into 2 times epsilon into ux, and V squared equals epsilon into capital V squared. This will help me to reduce into a form like this, suitable for the application of perturbation technique. So this again reduces to geometric series, provided you choose exponentials in the power of negative powers, of course. So you can notice that I have used u0 to be a0 into e to the power of twice. So power v0 I have selected as alpha minus c cube into t, cx minus c cube into t. So I can easily write it in this form, u0 and u1, u0 and v0. Next, I will just skip. So you can see that u1 will be a squared into 2c into e to the power of 4 times. Instead of 2 times, it will be 4 times. Instead of 1 time, it will be 3 times. Okay. So one will be in the even power, the another one will be odd powers. That's the beauty of it. So you come to the next level. So you will get e to the power of 6, and the other one is e to the power of 5. So you can put all of them together and do some induction technique. So again you have to do some high school mathematics. So you will finally get into that form, k squared, sigma k squared and sigma k. So you will get Vn to be like this. So all right. Yes. So I will be getting un is minus 1 power n, capital A power n plus 1, 2 into c e to the power of twice n plus 1. That's how you used to get 2, 4, 6, 8 like that. And Vn we used to get 1, 3, 5. That I have reflected here. Minus 1 power n, a power n, e to the power of 2n plus 1. Okay. So you can sum them. Sum you will get a neat exponential form. If you differentiate partially, you will get the secant hyperbolic square. And for the other one, we get like this. So the final solution is this. And both of them I have merged in the same graph, u and v. Thank you.
Thank you, sir. Any question? One or two? Okay, no questions. So
Oh, thank you.
let us thank the Rangarajan sir for his nice talk. Thank you. Thank you very much, sir.
Sorry.
So I request Ramanesh sir to hand over the memento as a token of gratitude.
Thank you. Photo. Oh, please. One ನಿಮಿಷ ಬನ್ನಿ ಬುದ್ಧಿ. You can hold it. Madam, leave it, hold it. ಬನ್ನಿ 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 ಸರ್ ಬನ್ನಿ ಈ ಕಡೆ ಬನ್ನಿ ಸರ್ ನೀವಿಲ್ಲದೆ ಹೀಗೆ ಥ್ಯಾಂಕ್ ಯು ಸೋ ಮಚ್ ಸರ್ ಇದೆಲ್ಲ ನೀವು ಪ್ಯಾಕ್ ಮಾಡ್ಕೊಡ್ತೀರಾ ಬನ್ನಿ ಮೇಡಮ್.
Hello. The next speaker is Dr. Veena Mattad from this next lecture. The speaker is Dr. Veena Mattad from the University of Mysore. She did her MSc and MPhil, PGDCA, B.Ed, PhD from our university, that is Karnataka University, Dharwad. Currently, she is working as a professor in the Department of Mathematics, Mysore University. Her main area of research is graph theory. She has guided the PhD students, gave invited talks in the various conferences, published more than 75 research articles. I take this opportunity to welcome you, ma'am, and I request ma'am to give the lecture.
Thank you, Professor Ramane, for the introduction. At the outset, let me thank the organizers of this conference for providing me an opportunity to come over here and discuss with you some of the recent concept that we have introduced. My intuition here is to reach to you the concept of eccentric weight of graphs, and I just define it and I'll just calculate it for some standard graphs and two graph operations. So I'm just going to deal with the elementary results regarding this. So let us start with what is eccentric weight of a graph. During Professor Ramane's lecture, we came across the concept of degree of a vertex, right? The number of edges incident with that vertex, okay? So once we have the degree of a vertex, we can talk about the eccentricity of a vertex. So before defining what is an eccentricity of a vertex, the concept of distance has to be considered. So here I am considering the simple graphs which are connected. Let us take that they have n vertices and m edges. So you take any two vertices, the distance between those two vertices is the length of the shortest path between them, okay? So that is called as the distance between those two vertices. And eccentricity of a vertex is the maximum distance from that vertex to any other vertex of the graph. And this concept of eccentricity is the probably one of the first distance based parameter introduced in the graph theory, and the mathematical definition is that it is the maximum distance from that vertex to any other vertex of the graph here. And if I consider the minimum of the eccentricities of all the vertices, that gives us the radius of the graph. And if I consider the maximum of the eccentricities of all the vertices, that gives us the diameter of the graph. And if the eccentricity of a vertex is equal to the radius of the graph, then we say that that vertex is a central vertex. And if I consider the set of all central vertices of the graph, that gives us the center of the graph, and it is denoted by z of z here. Okay. So in this graph, we have 10 vertices. So if I consider the vertex V1, the distance between V1 and V2 is 1, V1 and V3 is 2, and V1 and V4 is 3. Like that, we can calculate the distance between the vertex V1 and the rest all vertices of the graph. And you can see that the distance between V1 and V4 is 4. Okay, and the distance between V1 and V8 is 4, and that is the maximum distance of this vertex V1 to any other vertex over there. So the eccentricity of V1 is 4. Similarly, we can calculate the eccentricities of the other vertices, like V2, it has eccentricity 3, V3 2, and so on here. So now we say that a graph is self-centered graph if all vertices have the same eccentricity. Okay, in the previous graphs, you can see that the vertices do not have the same eccentricities, right? They differ. So it is not a self-centered graph. But if all vertices have the same eccentricities, then we say that that is a self-centered graph. Okay. So now we say that the vertex U is an eccentric vertex of another vertex, say V, if the distance between them U and V is equal to eccentricity of V here. Okay. So for example, if I consider this graph, right, so consider the vertex V1 and consider the vertex, I'll take the vertex V2 here and consider the vertex V10, okay. So if I consider V10, you can take the distance between V10 to V2, right. What is the distance between V10 to V2? It is 3, right. The path goes like this. V10, V9, V6, V2. Okay, the distance is 3 here. And what is the eccentricity of V2? It is equal to 3. So I can say that V2 is an eccentric vertex of V10 here. Okay, so we say that U is an eccentric vertex of V if the distance between U and V is equal to eccentricity of V here. Okay. But it is not the symmetric property, because as I said, V10 is eccentric vertex of V2, but V2 is not an eccentric vertex of V10, because the distance between V2 and V10 is not equal to eccentricity of V10. Distance is 3, whereas the eccentricity of V10 is 4 here. So this property is not the symmetric property here. Okay. Now, if U is an eccentric vertex of V, then by the definition, the distance between U and V is equal to eccentricity of V. Then the eccentricity of V will always be less than or equal to the eccentricity of U. Okay, and this is equal if and only if the other will be the eccentric vertex of this vertex. Okay, that is the remark from the above definitions here. Okay, so E is an eccentric vertex of G if V is an eccentric vertex of some vertex of G. In the previous slide, we saw that we say that U is an eccentric vertex of a V. Okay, here we say that V is an eccentric vertex of the graph if it is an eccentric vertex of some vertex of the graph here. Okay, so again, if I consider this, V1 is an eccentric vertex of G because the distance between V1 and V8 is equal to the eccentricity of V8. Okay, so there is some vertex in the graph, okay, which is at the distance equal to its eccentricity. Okay, that is called as eccentric vertex of the graph here. Okay, but V2 and V3, they are not eccentric vertices of the graph, because we do not find any vertices in this graph which are at a distance equal to their eccentricities here. So they are not eccentric vertices of the graph here. Okay. Now we call a graph as weighted graph if we assign weight to an edge of the graph, every edge of the graph here. So based on this thing, we have defined the eccentric weight of a graph. So let us consider the definition here. So consider a connected graph on n vertices and m edges. The eccentric weight of a graph denoted by EW of G, it is of defined as the summation of f of x for all edge x belonging to E. And what is this f? It is a map from the edge set to the set having elements 0 and 1. Okay, and how is it defined? It is defined as f of uv is equal to the modulus of the difference between the eccentricities of those two vertices. Okay, so if I consider the edge uv, then what is f of uv edge? It is modulus of eccentricity of u minus eccentricity of v. It is defined for all edges of G, and we take the summation of these values to get the eccentric weight of the graph here. Okay, so if I consider this graph, you can consider the edge v1, v2. Then the function value for that will be 3 minus 4 modulus, okay, that is equal to 1 here. So like that we calculate the function value for all the edges of this graph, and we sum up to get its eccentric weight as equal to 9 here. Okay, so we know that the eccentricity of any two adjacent vertices, they differ at most by 1. Okay, so either the difference is 0 or the difference is 1 here. So in that way, if we have the difference is equal to 0 for all the vertices of the graph, then automatically the eccentric weight has to be equal to 0 here. And if the difference is 1 for every edge of the graph, then the eccentric weight is going to be equal to the number of edges in that. So the bound, obvious bound for this is it lies between 0 and m. Okay, and they attain the lower bound and the upper bounds are attained for the complete graph and for the star graph. We will calculate them in the next slides here. So here we are going to consider the result. For any connected graph, the eccentric weight is equal to 0 if and only if it is a self-centered graph. Self-centered graph, as I said, all vertices have the same eccentricity. So when all vertices have the same eccentricity, when I consider the edge, the modulus of eccentricity of u minus eccentricity of v is going to be 0 for every edge. So the sum is going to be equal to 0. So we have its value is equal to 0. And again, if its value is equal to 0, then each function value for each of the edges must be equal to 0. When is that possible? When both the end vertices of that edge have the same eccentricity. So it will be a self-eccentric graph here. Okay. So this is the result. This is what I said, the proof of it. Okay. Now let us consider the graph G, and we'll remove a vertex from that graph, right? So when I remove that vertex, what will happen? The vertex will not go alone. It will go along with all the edges incident with that. Okay, when I remove an edge alone goes away from the graph. But when I remove a vertex from the graph, the vertex together with all the edges incident with that will be removed from the graph here. Okay, so what happens if G is a self-centered graph, right? Then the eccentric weight of that graph is 0, right? When I remove a vertex from that graph, any vertex from that graph, the possibility is that the remaining graph is again a self-centered graph, in which case the eccentric weight will be equal to 0 once again, or the resulting graph may not be a self-centered graph, in which case the eccentric weight will not be equal to 0, and it is not negative also, right? So eccentric weight of the resulting graph is either equal to 0 or greater than 0. So we can say that the eccentric weight of the graph G is less than or equal to eccentric weight of G minus V when G is a self-centered graph here. Okay, so that's the proof. So here we are discussing some eccentric weights of some of the standard graphs. So when I consider the cycle Cn, okay, cycle, a closed path we can consider, right? So vertex at v1, v2, vn, and eccentricity of every vertex in an even cycle is n by 2, and eccentricity of every vertex in an odd cycle is n minus 1 by 2. Anyway, whether it is n by 2 or n minus 2, this graph is a self-centered graph, and we know that self-centered graph have eccentric weight is equal to 0. So the eccentric weight of cycle is 0. When I consider the path, okay, again consider the path Pn. Okay, if it has odd number of vertices, if n is odd, it will have even number of edges. Okay, so when n is even, it will have odd number of edges here. Okay, so what happens here is when I have odd number of edges, start from this side and start from this side, okay, the values of the function will be equal to 1, 1, 1, because eccentricities goes on decreasing from here to here and here to here. Okay, when I come to the central vertices, eccentricity of the one central vertex is n by 2, eccentricity of the other central vertex is also n by 2 here. So the difference is 0. Okay, so in this case it will be twice 1 plus 1 plus 1. How many times? N by 2 minus 1 times plus 0, which stands for that edge between the central vertices here. So the eccentric weight of the path is equal to n minus 2 here. Similarly, when I consider n odd, then the path has even number of edges. Okay, so even number of edges I can consider break it into two parts. Okay, so that the function values of all the edges of left hand side is equal to the function values of the corresponding right hand side edges here. So it will be 2 times 1 plus 1 plus and so on. Again, how many times? N minus 1 by 2 times here. Okay, so that is equal to n minus 1. Okay, now we'll consider a double star. How do we get a double star? Take two stars, okay, say K1, R and K1, S, and join the central vertices by an edge. That gives us the double star here. Okay, so it is denoted by SNR, S here. And its eccentric weight is R plus S, because here we can consider two types of edge, vertices actually. The central vertices, what is the eccentricity of both the central vertices? It is equal to 2. Okay, if U is the central vertex of one star graph, its eccentricity will be equal to 2, because this distance from the other pendant vertices of the other star graph is equal to 2, and that is the maximum. Okay, similarly with the other central vertex V here, so eccentricity of U, eccentricity of V is equal to 2, whereas eccentricity of the remaining vertices means all the pendant vertices, it's equal to 3, because the distance between the one pendant vertex to the other pendant vertex, okay, that is equal to 3, because the path is from that vertex either V or U, or then U or V, then to the Ui or Vj. That is, so the eccentricity is equal to 3. So adding up the values for the function, we get its eccentric weight as equal to R plus S here. Okay, take any complete bipartite graph. Okay, we know that complete bipartite graph, the vertex set of it can be partitioned into two sets, right? And every vertex of one partite set is adjacent to the other partite set, and no two vertices in the same partite sets are adjacent. That is the definition of a complete bipartite graph here. And if I consider R and S greater than or equal to 2, each partite set have at least 2 vertices, then eccentricity of every vertex in that graph is equal to 2 here, and hence it will be a self-centered graph, and we know that self-centered graphs have eccentric weight is equal to 0 here. Okay, so what if I consider the generalized complete bipartite graphs? Not only 2 partite sets, I can consider finitely many number of partite sets. Okay, so in that case also it is going to be a self-centered graph, and hence its eccentric weight is equal to 0 here. Okay, so as a corollary to that, I can consider the star graph. One partite set have only one vertex, and the other partite set have greater than or equal to 1 vertices. Okay, so in that case the central vertex eccentricity is 1, and all the pendant vertices have eccentricity 2. So each edge function value will be equal to 1, 1, 1, 1. So when I add up, what will be the value? It is going to be equal to n, the number of edges in that central in that star graph. Okay, so consider the wheel graph. Wheel graph, we have seen the cycle wheel. Okay, so one cycle and one vertex which is adjacent to all the vertices on the cycle, that is the wheel graph. So the central vertex again has eccentricity 1, as it is adjacent with all the remaining vertices, and the eccentricity of the vertices on the cycles is equal to 2. So substitute these values by taking edges there in the graph. So we are going to get the eccentric weight as equal to n here. Okay, so if the graph is having m edges, okay, then eccentric weight of G is less than or equal to m minus the number of edges in the center of the graph. Center of the graph is the set of all central vertices of the graph. Okay, so central vertices again, it's their eccentricity is equal to radius of the graph. Okay, so when I consider the induced subgraph on the center of a graph, it is a self-centered graph because all the vertices are having radius equal to radius. So eccentricities are same. So it is self-centered graph. So eccentric weight of that graph is equal to 0. Hence eccentric weight of G matters with the edges of the G which are other than the central, the edges joined by the central vertices of that graph. So it will be m minus that because that is equal to 0 here. Okay. So if eccentric weight of G is equal to m, where m is the number of edges in that graph, then again the central center of the graph gives us the totally disconnected graph when I consider the induced subgraph on it. But the converse is not true. For example, if I consider this graph, okay, so the two vertices in the middle part are the central vertices. So center of the graph is set of those two vertices. When I consider the induced subgraph on them, we are getting it as 2 into 2k1, right? This totally disconnected graph, but its eccentric weight is not equal to m. You can calculate the eccentricities of each of those vertices. Eccentricities of the top vertices 1, 2, 3, 4, 4, 4, 4, 4, right? 3, 3 and 2, 2 here. Okay. So the difference when I consider, we are not getting it as equal to m. It will be less than that here. So the converse of it is not true. Okay. Now we will consider the two operations here. One is join of two graphs and product of two graphs. So join of two graphs, take two disjoint graphs. The join of those two is obtained by putting them together and joining every vertex of one graph to every vertex of the other graph. That is the join of two graphs here. Okay. So vertex set is union of the vertex sets of both the graphs. And edge set is edge set of G1 union edge set of G2 together with all edges which are joined by every vertex of G1 to every vertex of G2. This is how the join graph is obtained. And if G1 and G2 are disjoint non-trivial connected graphs having no full degree vertex. No full degree vertex means if a graph is of order n, number of vertices is n, then if I have a vertex of degree n minus 1 there, then that is called as full degree vertex. Okay. So if a graph has no full degree vertices, then its eccentric weight is equal to 0. Okay. So how do we justify it? Consider the vertex sets of both the graphs as like this. Okay, and they do not have full degree vertices. So degree of every vertex there is greater than or equal to 2 because and the degree of other vertices here in the other graph are also greater than or equal to 2 here. Okay, and when I consider G1 plus G2, what is the vertex set? All the vertices of G1 and all the vertices of G2. Okay, and distance between the two vertices from one graph to the other is 1 because every vertex here is made adjacent with every vertex there. So the distance between from this vertex to all the vertices in the G2 will be equal to 1. Similarly, the distance between all the vertices from G2 to G1 will be 1, and the distance between a vertex from one vertex of one graph to the other vertex of the same graph G1 will be equal to 2 here. Okay, so it is true for both the graphs here. So when I consider the eccentricities, I am going to get ui vi is equal to 2 and ui vj is equal to 1 here. So the function value is going to be equal to 0 for all uv belonging to the edge set of G1 plus G2, and hence it's going to be equal to 0. Now when there is as a particular case of that, instead of considering G2 as a general graph, I have restricted it to K1 here. Okay, so for any graph G whose maximum degree is less than n minus 1, again no full degree vertex. Okay, so eccentric weight of G plus K1 is equal to n here. Okay, it's a corollary to the previous result because the vertex set of G2 is having only one vertex and that is adjacent with every vertex there in the other graph. Okay, so that will be having eccentricity 1, all other vertices in this place will be having eccentricity 2, so the difference is going to be 1 there. Okay, so that is equal to n. okay, the number of edges in that graph. Now, if G has k full degree vertices, okay, in the previous results we considered having no full degree vertices. So, if G has k full degree vertices, then the eccentric weight of that graph is k into n minus k. So, consider the graph, if k is the number of full degree vertices of the graph, then degree of those many vertices is n minus 1 and degree of the remaining vertices is less than n minus 1. So, that degree of the earlier k vertices or eccentricity of the earlier k vertices is 1 and eccentricity of the remaining vertices is equal to 2 here. So, when I consider all the edges here, one way we are getting 0, the other way we are getting 1 here, and when I consider from here to here, it is again equal to 0 here. So, when I add up all these things, we are going to get k into n minus k here. Okay, so it's a corollary to this, substituting k is equal to 2. That's what we are getting here. Eccentric weight of G, which is isomorphic to kn minus e, where e is an edge of that graph. Okay, it's going to be 2 into n minus 2 here. Okay, so again, as a corollary to the same result, if G1 is a graph with m vertices, again having, yeah, I'll finish, sir. So, S full degree vertices and G2 having T full degree vertices, then eccentric weight is weight of the joint graph is given by this formula. So, I'll skip the proof here. Yeah, here we are considering the product of two graphs. Again, take two disjoint graphs G1 and G2. Okay, the vertex set of the product graph is V of G1 cross V of G2, the Cartesian product of the vertex sets, and two vertices are adjacent. If two vertices u1 is equal to v1 in the first graph and u2 is adjacent to v2 in the second graph, or u2 is equal to v2 in the second graph and u1 is adjacent to v1 in the first graph. That is the product graph of two graphs. And one observation here is that the eccentricity of any vertex in the product graph is the sum of the eccentricities of the entries in that pair in their original graph. So, with the help of this, we can calculate the eccentric weight of the product graph, and it is obtained like this. Modular the cardinality of the vertex set of H into eccentric weight of G plus the cardinality of the vertex set of G into eccentric weight of H. So, this is the proof. I'll skip the proof here. Okay. So, for any positive integer, there is always a graph whose eccentric weight is equal to n here. Okay. So, what is that graph? It is the Sunlet graph we can get. How do we obtain it? Consider the cycle, okay, having the vertices v1, v2 and so on, vn, okay, and then add new vertices equal to the number of vertices there. The pendant edges can be included at each of those vertices, and that is called as the Sunlet graph here, okay. And this graph has eccentric weight is equal to n, okay. It can be calculated with by calculating the eccentricities of all the vertices and by taking the edges in that graph. So, this is, and again for n is greater than or equal to 4, the positive integer, there exists at least two graphs whose eccentricities are equal. Okay. So, I can consider the graphs star graph and the wheel graph. They are different graphs. Okay. They have the same eccentric weight here. Okay. Yeah. I am considering the unicyclic graph. A graph which has only one cycle is called as unicyclic graph, and the speciality of unicyclic graphs is that it has equal number of vertices and edges. Okay. So, for unicyclic graph, we have the bound for eccentric weight of graph as m minus p, where Cp is the only cycle in that graph, and again we have considered that's the proof. I'll skip the proof, it's a lengthy proof also. Yeah, I think this is the last result. It is just, we have just introduced the concept of eccentric weight here, and elementary results have been studied. It's much more to be done on this concept, and it is open for everyone. Thank you.
Thank you, ma'am. Any question? Madam, one question. Eccentric weight of G1 equal to eccentric weight of G2 you are done. Means there is a graphs. Is there any characterization or any some sufficient condition like that?
These are the only results for here. That's why I thought let me open it
Thank you, ma'am. So let us thank the madam for a wonderful lecture. Thank you very much. Hello. Now the next speaker is Professor S.C. Siraj Shetty. Professor S.C. Siraj Shetty, he is a colleague of mine in my department at Karnataka University, Dharwad. He has completed his BSc, MSc, MPhil, PGDC and PhD from the same university, Karnataka University, Dharwad. Currently, he is a professor of mathematics in the Department of Mathematics, Karnataka University, Dharwad. He has published more than 180 papers, delivered many talks in the various conferences. He is a very energetic man and he has guided 11 PhD students so far. The main area of his research is numerical analysis, wavelet analysis, fluid dynamics. I take this opportunity to welcome you, sir, and I request Professor S.C. Siraj Shetty to deliver his talk.